Welcome everyone to a more fun live stream here. Breaking news. What I brought to you today are presentation slides from yesterday. I was joining there some webinar of SiFive here of previous live streams already having the SiFive Hi5 unmatched, and previous videos in general. You've seen this here, recurring viewers and subscribers, using x86 for most part of my life, growing up with it, but not the greatest fan of the over complexity that is Intel's and AMD's and clones x86 architecture. Huge fan of RISC, in particular the cleanliness and new start, fresh start, and vector extension, previous instruction set architecture videos. So what SiFive presented yesterday is new performance family. By the way, is this correctly sorted? I hope so. Or is it? Maybe I should have checked that though. Yeah, just. So I made some screenshots there of this webinar. So far they have mostly what was the initial? So the last was unmatched. Unleashed was the first thing. They have funny names. I think $999 US. Unmatched, the board, mini ITX board, previous video. U7 something SOC, a little bit funny name, $666-ish. And of course these boards are for developers, early adopters, for evaluators. If you are Samsung and Western Digital and design your hard disks and cellular broadband stations with that and stuff, not necessarily for normal users. So the new, previously microcontrollers in the U series. So what is new is their yesterday or so publicly announced performance series, highest performance, most advanced RISC-V processor available. The funny thing is, on some news sites the other week people were fighting with me. RISC-V is only for shabby microprocessors and will never have rivaling x86 performance. And I disagreed with that, and also maybe not the best time spent on this comment there. I always said in the previous instructions architecture, as far as I can see, RISC-V made similar to other RISC architectures, Spark, PowerPC, ARM to some degree, but not the most risky. The reduced instruction set, much easier to widely decode. There, as seen in Apple's M1, was it 6 issue, 6 or 8, maybe 6. The latest Epic thread ripping x86-3, or the latest Intel maybe 4 byte issue, meaning how many instructions issued at one clock. And due to that, I expect RISC-V, especially with a vector extension, to reach high performance levels comparable in a couple of years. Of course, these are startups and universities and a free collaboration with other like open source folks doing this for FPGAs. So this cannot be compared to 40 years of R&D at Intel, because all the stuff like inner workings need to be reinvented, especially avoiding patents there in this area, not to get sued by Intel and AMD and stuff. So what is new? The performance SOCs here, or cores P550, P270, highest performance RISC-V processor on the market. And they said the design is finished and it's already in the design hands of their customers. They also said they had over 200, probably 201 or 205, I guess, 200 design wins, probably something they didn't call names, but I suspect stuff like Western Digital or NVIDIA and similar stuff of having this for SSDs or hard drive controllers, and NVIDIA, I think, RISC-V for, although maybe this changed to ARM now, but as far as I remember, even NVIDIA had RISC-V for their power management controller there. So the Hi5 unmatched, the U series, U7, has a, I think, 7-stage pipeline, dual issue in order. They also have a U8, so U8 was, I think, announced last year, but of course, if you finalize a design, it still takes like a year with customer designs and taping that out. Customer designs at Samsung or Qualcomm or whatever their 200 or NASA, random stuff, right? I'm not saying those customers, just like examples of like car manufacturers and all this kind of customers they could potentially have. And so that is, we have not seen that yet. Even their unmatched took like probably a year to get in our hands. So as usual with electronic design, prototype, or also first the silicon tape out testing, another spin, some bugs. And so why does it take a year or two to get into the market? Because design, right? So up from U7 7-stage, I think, dual issue, so that performance, and the U7 is in order. So they also have U8. I think U8, not sure what that was a dual issue or triple issue, but I think the U8, as far as I remember, is already out of order, and the SiFive Performance P550 also out of order. So 13-stage triple issue. Triple issue is actually on par with AMD Zen, as far as I remember, as issuing 3 instructions per cycle. Out of order microarchitecture with private L1, L2 cache, and reaching 2.3 gigahertz allegedly and 7 nanometer typical process there. They also have a SiFive Performance P270. I found this a little bit confusing. You will see in a minute why. Because so they say P, of course, larger number, more performance. However, there's one big difference. So P550 highest performance and P270 balanced design. The big difference is here the vector extensions. So to my surprise, the highest performance does not have a vector extension. Not really sure why, but maybe this is customer demand or just starting one project and then the other. Maybe they started P270 first and then did redesigns and something of that sort. So the P270, confusingly, you would think this is the same pipeline, but their stuff previously, their cores, has been highly configurable. Maybe this is why, or similar in open source cores, you can tune certain parameters in the synthesis process there, just as we have done on FPGAs in previous videos here on this channel. So that probably configurable 8-stage, 13-stage, depending on, for example, not sure what their design, they didn't disclose that, but whatever the design criteria have been. So a big difference here in the number of stages. Of course, this has another penalty for jumps or mispredictions there for out of order execution. But this P270 confusingly comes with a vector extension. So further then, so these are their details. So this is RISC-V instruction set architecture, as I've presented in the previous video. So this is RV64, so RISC, that means RISC-V 64-bit G general for integer, atomic, float and double, and bit manipulation and compressed. So C is compressed, similar to what we've done on a PGA. So what is new is B for bit manipulation. So that would be one of the first cores. Bit manipulation has stuff from pop count, but also other popular stuff like rotate. Surprisingly, the core RISC-V base either doesn't have rotate, to my surprise, but also other shuffle permutations, fun stuff. Probably want to watch some of Claire's presentation, who is one of the authors of the bit manipulation extension. And so a current multi-core with up to 4 cores in a core complex private L1, L2 caches and configurable L3 cache. Sophisticated trace and debug capabilities, as you probably would need in such a complex project, obviously. And optional cryptographic accelerator. So that is optional, meaning here hardware cryptographic accelerator. They didn't disclose more, I think, but configurable, of course, if you are a customer of them and want to synthesize this stuff and ship it in an ASIC, you can configure that, tick that option. Have that or not, of course, it comes with certainly quite some penalty of hundreds, thousands of logic gates. So this is their block diagram here. So for cores, MMU of course, this also has a larger SV48 virtual memory. I think the previous was what is the other SV37 or something of that sort. So larger physical address space for mapping really large artificial intelligence and other scientific stuff. And yeah, they also, so performance numbers, this stuff is a little bit tricky, right? This is of course the usual, of course I'm not falling for this expert in this area, not falling for this marketing tricks. This is of course marketing tricks just like Intel and AMD or VR and stuff would do, because you would think, hey, 3 times more performance, but no, of course, not so fast. This is spec int 2006 per area, so this is only for in half of the area highest single thread performance they claim. Here C is C++ only in the spec, probably the other stuff was Fortran or something they said. It's like, yeah, what they think is more. I mean, of course, right, they only benchmark what is beneficial to them, but I think the other stuff is probably Fortran, correct me if I'm wrong. I would agree though that yeah, C++ obviously what most people use. Maybe they also don't have the best Fortran compiler, right? It's probably LVM Clang or GCC, so Fortran is like, yeah, probably a little bit lacking. But anyway, so high single thread performance, that is of course amazing, but this 3 times only compared to ARM Cortex A75, of course, also a 3-year-old or so design at ARM, so comparing this year's or last 12 months design with 3-year-old design plus, this is not raw performance but performance per area, but this only, so that means it's apparently half the area, which certainly ARM a little bit more complex. I said initially, we also looked at this in detail, previous video, ARM instructions and architecture. They have a little bit more RISC features of auto increment and other. Previously in ARM 32-bit had a lot of more conditional bits. ARM64 did mostly away with that, but still some kinds of included, I believe, shifts and increment of registers and stuff certainly makes the microarchitecture a little bit more complex. Plus, of course, they might have already, all right, this is P550. The ARM core probably has a little bit more SIMD, single instruction multiple data. But yeah, so comparing apples and oranges as usual. And again, yeah, not 3 times faster, only 3 times higher performance per area. And if it's already half size, so then half size, same performance would be 2 times. So yeah, probably the raw performance should still be quite good. Also, yeah, I wish they would, as usual, Intel also does this, Intel and AMD, right? Are not publishing raw numbers because yeah, probably the devil is in the detail and the performance. Performance will be better than the unmatched NU7, but sure, I am certainly aware this is a startup. They are starting from scratch for like probably a decade now. So yeah, they also claim a substantial memory performance. The U7 not yet as amazing that we have here on the desk right now. So the P550, 20 gigabyte per second copy performance, data cached in the 3 cache L2 gigahertz. They say a single P550 core can exceed the capabilities of a DDR4 controller running at only 2166 megahertz. And so yeah, this is one core plus of course cache, but of course normal applications. This is again just some raw performance numbers. Intel and AMD ARM CPUs of course have similar numbers, and most people don't care about this kind of cache numbers. This is just some throwing big numbers because most applications don't mem copy all this stuff but have more sophisticated application logic. Just putting this, of course, they always present this as it's the most amazing, but just trying to be a little reasonable and put some guidance here to this raw numbers. The P270 performance core here, the big difference here is the vector unit extension, RISC-V vector. They implement RVV, so RISC-V vector RVV, 1.10 release candidate. It's of course a little bit dangerous to implement a release candidate that they are now taping out with customers, I guess. So on one thing, I would not expect any major changes to the vector extension. On one side of the coin, it is amazing to see to have finally RISC-V vector extension. Previous video, huge fan of that, looks amazing on paper, implemented in real hardware. On the other, it's like, yeah, the standardization process was a little bit long. Of course, a lot of computer science and different companies working on that. So yeah, standardization process like C, C++ and USB and takes a while. And the end effect is, yeah, the first vendors implement a release candidate. That is, of course, a little bit unsettling, but similar, yeah, probably release candidate is final, supposedly final, and yeah, would be amazing to get my hands on this though, if someone from SiFive watches this live stream here. If you have some early prototype stuff, would be amazing to do some testing, programming and Linux enablement with that. Feel free to send one board there, because unmatched we purchased with our own hard-earned money. So yeah, RISC-V, as I said in the beginning, a little bit puzzling to me that the P270 with a lower number has the vector extension and the P550 does not. Probably two different teams or different customer inquiries, maybe one yeah, or configuration, and then it doesn't reach the target clock speeds, frequencies, who knows what, something of that sort. We should, let's by the way check quickly. So yeah, actually the P550 also with B4 bit manipulation, so at least pop count, shuffle stuff and rotate and instructions like this also in the P550. Otherwise, yeah, this looks quite similar. Obviously, hardware cryptographic accelerator, and here's the big difference, the vector computation unit. They implement a 256-bit wide vector single instruction multiple data here with an supported element size, as this is more forward scaling. I had a detailed video about that previously. 8-bit, 16-bit, 32-bit, 64-bit, integer, and 16-bit, 32-bit. This is like double, half, and wait a second, how to say it? Double, yeah, double float and half, and as well as fixed point, 8.8, so 16, 8.8 into Q15 fixed point. Vector types as more freely scalable. The point of this, but details in the previous video, is similar to what ARM also implemented with a scalable vector extension in a similar concept, probably all dating back to Cray or Fujitsu and similar vector stuff in the 80s. Even I think Cray had sort of kind of this vector stuff in concept, so that unlike Intel's MMX, AMD3 now, then SSE, multiple variations to AVX and AVX 512, where you specifically need to write new code. This is supposed to be forward compatible in scale, so when future silicon implements 512 bits, it basically doubles the performance for free, because due to the way these instructions are encoded and automatically scale for setting an element size and then just automatically processing with all the additions, multiplies and shuffling and stuff, twice as many elements per cycle with potential future wider vector extensions. So yeah, as we saw earlier, 8-stage dual issue, although wait a second, so the vector, as I say, vector pipeline is decoupled, 9-stage, Scala pipeline, 8-stage dual issue in order. Actually, need to check that. Did we see that in an earlier slide? Right, they disclosed that here. So 13-stage out of order versus 8-stage in order. So yeah, it's a little bit odd design choice. I would probably personally not necessarily have done that, although I don't know their customer and inquiry demand criteria a little bit, because you have the lesser performance Scala design with the like in order with the vector extension. But of course, in coming years, of course, they will each year, similar to AMD and Intel and ARM, every other year have performance increasing microarchitecture improvements to come. Performance block diagram here, the instruction front end and the decoupled vector unit here, meaning running decoupled of doing the vector math there. 128-bit ALU pipeline here, so probably I would suspect, as this has implementing 256, so this means similar to AMD's implementation of AVX, also needing twice as long or something, processing all the stuff like twice as so to process 256-bit in a 128-bit ALU or something of that sort, I guess. Load store queue, 128-bit cycle, here L2 cache, and performance-wise, they compare that to a Cortex A55 and they claim 20. Also, again, comparing this to a couple of years older, before the people on some new sites shout at me, but ARM is better. No, they are just 30 years in the market, and these are new startups who need to build all the architecture, microarchitecture, and just ramp their stuff up, similar what ARM and Intel have done for 30 and 40 years. So yeah, vector processing in a small package, 0.3 millimeter squared in 7 nanometer, and yeah, 20% higher performance. It's of course funny, this is what I meant with marketing tricks here. The previous diagram used performance per area. Here they compare directly the performance. Again, probably choosing to have the highest graph here to represent their best marketing material. So 20% higher performance in single thread performance, 4.6 spec in 2006 per gigahertz, geometric mean, and again C++ only, your mileage may vary and that stuff. They also have some conversion tool which is quite nice. They named Recode, unfortunately, because it is a name I also wanted to use actually, and I only didn't use because there was previously this Recode magazine stuff there. What was it, Wall Street Journal or something? Anyway, LLVM based Recode tool to automatically transition previous code. Also maybe this is on the next slide. This slide just realizes this a little bit ahead. So this slide is only, they have LLVM suite, it's auto vectorizing, probably could see some improvements. And so yeah, LLVM auto vectorizing code today, allegedly somewhere there, probably need to peel those patches out there and add them to our T2 distribution, and otherwise rewritten using C in Strinsics there, as you would otherwise do with AVX and ARM scalable vector extension as well. So handwritten, hand-tuned code as usual can be at times a little bit tighter. And do we not have, did I not have, where is this Recode stuff? Did I not make, maybe I didn't, maybe I forgot to make a screenshot. Then, as I said, they have a Recode tool to transform ARM Neon. In this LLVM suite, they had an example. It's as easy as -- Recode equals Neon, I think. They said maybe if there is demand, they implement more, like x86 or something. And probably this should be open source, so maybe some open source toolchain could be there for others to improve, for in general in Strinsics conversion between different instruction sets. But in general, most people of course use auto vectorization and don't bother with hand optimizing this stuff. So their outlook today, they presented Soul's performance course, which is of course nice to see. Later this year, higher core counts, then quad core, world guard, system security, whatever, probably some secure boot kind of whatever stuff. And then of course 2021 next generation out of order, as I said, as all companies, not a secret, Intel, AMD, ARM. So SiFive always working on the next big thing. So more next generation out of order microarchitecture stuff to come. P5000, no surprise, of course, they add vector compute there as well. And virtualization, similar virtualization extension, also delayed. The usual problem of design by committee. Those folks here, SiFive, other universities and other open source folks and companies sitting there on a table discussing with meetings and flying around the world with some good coffee, chatting about how to precisely to do that. And as you would expect, standardization. This Take some time. I think this is not yet release candidate. I wonder, however, if we will see KVM Linux-based kernel-based virtual machine support for virtualization of RISC-V without virtualization extension, because as far as I've seen, RISC-V should meet this virtualization theorem there, so that you could trap and emulate in the kernel, of course, with maybe 90% instead of 98% performance, similar to probably PowerPC and some other architectures have seen. And yeah. Anyway, so yeah, virtualization, that is as usual, no secret there. There will always be next big thing. So yeah, essential, the usual stuff here, you guessed it, marketing slide, something, and embedded. But that is not all. Last but not least, there's also from Russia, just in the news today, from their Rostek department, RISC-V to come. Previously, they were working, was it MIPS? At least China was working with MIPS. Not sure. But their other stuff was a very large instruction word, some was so architecture. And now they announced just now this Rostek conglomerate, their state-backed corporation specialized in technology, penned a deal with the server company Yadro, silicon design company, to develop RISC-V processors by 2025, apparently something. 30 billion rubles, 400 million in US greenbacks. 60,000 systems planned. I wonder if of course this is just some alternative systems. Probably not something you and me will see. I also not have seen this previous Elbros systems there. They had some very large instruction words. So what they are planning is 64 RISC-V compatible application core, general, so IAFD, A for atomic and float and double, and C for compressed, U-arch, flexible U-arch template. Maybe they recycle their Elbros very large instruction word stuff, 10 to 12 stage pipeline, user, supervisor, machine mode, privilege levels. As this is general something, of course, it's Linux compatible. That is not a new feature. That is just fact of being RV64GC, or G for that matter. Anyway, memory management unit, no surprise there. Caches, no surprise. Caches, hardware atomics, that is A extension there of G, of I, A, F, D extensions, A for atomics. ECC, high performance, IEEE, compliant floating point unit, no surprise there, just what you would need today. So yeah, there is more stuff coming. So yes, Russia also, so I guessed that or remembered that correctly, that was previously MIPS, and very large instruction set architecture here, what some custom stuff that they claim is amazing. I have not seen it. If someone there from Rostek or Russia is watching, I'm sometimes in Moscow, so if you want to show me this stuff in Moscow or want to send one of this Russian Elbros, something 2K family there my way, you're welcome. Happy to take a look and support this in T2. Otherwise, not expect to see this anytime soon. But the point is, there are alternative implementations, including from Western Digital and Samsung and who not, and open source. Claire's Pico RV32 or new Pico, what is it? The new one, Pico, just Pico RV, something of that sort. Plus the DEX, RISC-V and others. And that is the beauty of this. Not only you and me can work with those people on the instructions architecture and guide them, for example, with the, as far as I've seen, amazing vector extension and scalable and forward compatible vector extension, but also virtualization and stuff like, not unlike x86 or ARM, where the big companies dictate what is done. Open discussion, open community, and open source and freely usable. So you and me can implement a processor if we wanted to, or here in Europe or the States or Russia, and have compatible processors, not like x86 or ARM, where you cannot do that without licensing that from Intel or AMD. Anyway, that's it what I wanted to summarize for today. I am certainly thrilled. As I said, the SiFive unmatched so far here on my desk, a little bit Intel Atom AMD E350 performance, but so yeah, not for your epic thread-ripping gaming workstation, but that's certainly coming in some years' time. So far we have some reasonable fast thin client-ish workstation. Hey, and since yesterday I have Emacs running, so I can actually freaking properly program on that. That's what I wanted to summarize for you today. Certainly also interesting to see how new architecture, even open architecture, is standardized and developed, and see this growing in higher performance, and that's certainly interesting to come. And we will also continue with that here on our FPGA previous video, and write some nano and microkernel firmware and operating system from scratch. Comment there in the audience. Hope get some socket-based RISC-V desktop CPUs similar fast as current Core i7 Ryzen 7. Socketed, not sure, maybe not, but for sure. So even the next year's, even this or the next year's performance is of course not yet epic thread ripping, but as I said, the last year's U7, or no, probably in the meantime 2-year-old design U7 SiFive unmatched U7 Atom performance, of course disappointing for most people, but hey, I can work on a terminal, so and I can move Windows around, hardware isolated, so that's fine for that. Even that will not be epic thread ripping. It will be a huge step forward. I think the U8 is 2.3 times the performance, and that might also again be 2 times the performance. So, but again, this is certainly, especially from the clocks, 2.3, I think they mentioned here somewhere, yeah, 2.3 and 7 nanometer. So it will be faster for NAS and network appliances and stuff, and people who don't AAA game and browse the internet all day on YouTube or something, it will be high performance, it will be even more usable, but it will, I'm not setting here false expectations, it will not yet be that flagship performance, enthusiast performance that will probably be around 2025, but truth be told, Intel and AMD, well, at least AMD, Intel standing a little bit still, well, maybe they have something new until 2025, but AMD certainly not standing still, so they of course will increase the enthusiast epic thread-ripping performance. So by 2025, the RISC-V startups will have catched on, but given that AMD and Intel are not standing still, the gap might be narrower, the gap might be smaller, but there will still be quite a significant gap, simply because these companies have 30, if not 40 years to catch up. Of course, nowadays designing a new silicon, as seen on this channel with the FPGA, is much easier, better tools, faster computers, epic thread ripping and stuff, but re-implementing all this out of order execution, vector extensions, of course not an easy task, needs quite some handful of engineers to work all day, night and weekend long for years to implement this, synthesize this and bring this, tape this out to ASICs. So it is for me no surprise that it takes years, and yeah, as I said, I think next year's stuff hopefully should be faster, as seen in this presentation. 2025 probably pretty beefy high performance stuff, and certainly I always said my guesstimate is it takes a decade to catch up, simply because Intel and AMD, as I said, are not standing still and continue with this stuff. But it is nonetheless for me nice to have more alternatives, because PowerPC is of course mostly standing still, Spark mostly up and down, and ARM certainly something but not open. So from that open perspective and options, that is of course a nice long-term option, especially for new startups. Think getting silicon back into Europe here, and having independent European researchers or Asian or US and so on, new startups to create processors, AI accelerators. All right, I think some slide probably somewhere mentioned, I think they have AI, I forgot this. So they have somewhere, maybe I didn't make all screenshots here of their presentation, but somewhere they also had AI, somewhere, was it not on the slides? Maybe you serious something. ES, deterministic course, RTOS, high performance, S7, whatever, something. They had here somewhere also some AI, like neural network extension with their proprietary AI accelerator. Not sure which of those. Maybe RISC-V. Where did the hardware? No. They had some, I think it was intelligence extension, so they're not sure how proprietary that is. But yeah, of course, these companies are want to make money. So these are not open source designs, so not to mix that. If you want to spin your own course, this is not GPL open source or BSD, MIT open source design. This is their proprietary design. You need to design your own or license it from them or others, not to mix that. So from that perspective, we are not really closer to an open source CPU. If you want that, of course, there are like Claire's Pico RV, but this is Pico, right? Not out of order speculative execution vector extension. But at least there is something open source that you can run at 50 megahertz or so on your faster on your FPGA. But as people have done, also VEX, RISC-V and stuff, you can do this. Sure, you can also do this. They are open source, Spark and even 486 by enthusiasts. But this is, of course, you can't sell an open source like 486 thing unless all patents expired. Also not that interesting. Open RISC-V, sure, there are other stuff, but RISC-V, of course, many nice performance attributes over Open RISC-V. So let's see, one more comment. Could you please provide slide in PDF form? I don't really want to share that. Thanks for asking. I think they will present something on their website. I just made this are just screenshots here, so, and they're not my slides are only reiterating the marketing stuff. But otherwise you have them in the video, I guess, and I think they will put the whole webinar in video form there. I'm not sure if they put the slides up there. But anyway, you have some most of the useful slides you have here in this video. Don't forget to share, like, and subscribe. And I hope to see you soon for the next technology updates and fun coding stuff to come.